Have you ever just stared at a huge, chaotic pile of data and wondered, how on earth do I make sense of this? How do I turn this mess into something clean, elegant, and efficient? Well, that's a classic challenge in programming. And today, we're going to see how finding the perfect tool for the job can make all the difference.
So, let's imagine this. You've got a massive list. We're talking millions of numbers. And your job is to find two of them, just two, that add up to a very specific target value. Now, how would you even begin to tackle that? You could check every single possible pair, but that would take forever. It's just wildly inefficient. There has to be a better way, right?
To figure this out, we're going to dive into a classic coding problem, one you see all the time in technical interviews. It's called the sum-pair problem, and it's the perfect way to see completely different problem-solving strategies in action.
Okay, so here's the official setup. We're given a sorted list of unique numbers. Let's say it's 1, 2, 4, 5, 6. Our mission is to find two numbers in that list that add up to a specific target. Let's go with 7. Pretty quickly, you can probably spot that the answer is 1 and 6, but the real question is, how do we get a computer to find that pair efficiently?
Well, one pretty common way to do it is with something called hashing. You can think of a hash map as like a little notebook. As you walk through the list, one number at a time, you calculate its complement. That's the other number you'd need to hit the target. Then, you just peek in your notebook. Have I seen that complement before? If the answer is yes, boom, you found your pair. If not, you just jot down the current number in your notebook and move on to the next. It's a solid method for sure. It works. But there's a catch. This hashing approach has what we call a space complexity of O of n. All it means is that our notebook has to get bigger and bigger as our list grows. If you have millions of numbers, you're going to need a massive notebook, and that uses up a lot of extra memory. So what if there was a way to solve this just as fast, but without using barely any extra memory? Something with what we call O of 1, or constant space.
Turns out there is, and it's an incredibly elegant algorithm known as the two-pointer technique. Honestly, this is one of those aha moments in coding that really can change how you think about problems.
The whole idea is just beautifully simple. Instead of looking at one number at a time, we're going to use two pointers. We'll stick one right at the beginning of the list and the other one right at the very end. Then, we just start moving them toward each other, intelligently narrowing down the search until we either find our match or the pointers cross paths.
Let's watch this thing in action. Okay, same list, 1, 2, 4, 5, 6, and our target is 7. We start with our pointers at 1 and 6. So what's their sum? Well, 1 plus 6 is 7. And would you look at that? On the very first try, we found the pair. How cool is that?
Okay, that was a bit easy. What if the target is 9? We start in the same place, pointers on 1 and 6. The sum is 7. Now, 7 is less than our target of 9, so we need a bigger sum. Think about it. If we move the end pointer from 6 down to 5, the sum is just going to get smaller. That's the wrong direction. So our only logical move is to take the start pointer and slide it forward from 1 to 2, hoping to increase our total.
All right, so now our pointers are sitting on 2 and 6. The sum is 8. We're getting closer, but it's still too small. So we apply the exact same logic. To get a bigger sum, we have to advance that start pointer again, moving it from 2 up to 4.
And here we are, the final step. Our pointers are now at 4 and 5. What's their sum? It's 9. We found it. Do you see what happened? We never had to check every single combination. We just intelligently and systematically closed in on the answer. It's an incredibly efficient way to solve this.
But, and this is a huge but, there is one critical catch. This whole brilliant technique only works if the list is already sorted, right? If the numbers were all jumbled up, moving the pointers wouldn't tell us anything useful. We wouldn't know if we needed to find a bigger or smaller value. The whole logic falls apart.
And this, of course, leads us to a new, much more fundamental problem. What happens when the data you get in the real world is a complete mess? Before we can even think about using our slick two-pointer trick, we have to clean up the room first. We need to sort the data.
So that just raises another big question, doesn't it? Our data, in this case, is in a linked list, which is a bit different from a simple array. And remember our goal. We want to avoid using a ton of extra memory like we did with that hashing approach. So the real challenge becomes, how do we sort a linked list efficiently, in place, without having to create a giant new copy of it?
The answer is we build the right tool for the job. And when it comes to sorting a linked list efficiently, one of the absolute best tools in the entire shed is an algorithm called merge sort. It follows this powerful, almost poetic paradigm. Divide, conquer, and merge.
The strategy behind it is just beautiful. First, you divide. You just split the list right down the middle into two halves. Then you conquer. You do the same thing to each of those halves, and the halves of those halves, and so on, until you're left with a bunch of tiny lists with just one element, which, by definition, are already sorted. Finally, you merge. You start combining these sorted little lists back together into bigger and bigger sorted lists until you have your final, fully sorted masterpiece.
Now, that merge step is really the heart of the whole operation. Just picture two lines of people, and each line is already sorted by height, shortest to tallest. To create one single sorted line, what would you do? You'd look at the person at the front of each line, pick the shorter one, and tell them to join the new line. You just keep doing that over and over. That's exactly how the merge step works with our data. It's that simple.
And the result of all this? For linked lists, merge sort is unbelievably efficient. Its time complexity is O of n log n, which is pretty much the gold standard for sorting algorithms. But crucially, its space complexity is O of 1. That means it uses a fixed, tiny amount of memory no matter how big the list gets. We're just cleverly rearranging the existing pieces, not making a bunch of new ones. So we get our perfectly sorted list without that heavy memory cost.
So let's just step back for a second and look at the big picture here. Let's see how this all comes together to build a really powerful problem-solving toolkit. Because we didn't just solve one problem, did we? We solved a problem that unlocked the solution to our original problem. Let's just quickly recap this whole journey. We started with the sum pair problem, but we hit a snag, a complication. Our data was a jumbled mess, and that stopped us from using the most elegant solution. So what did we do? We built a tool. We used merge sort to get everything organized, and once that was done, we could finally unleash that super fast two-pointer technique to get our answer.
So what's the really big takeaway here? This whole process, it shows off some really core principles of programming. First, having organized, sorted data can unlock incredibly powerful shortcuts. Second, you can often solve really complex problems by just breaking them down into smaller, simpler ones. And finally, choosing the right algorithm for the right data structure, that can make a world of difference in how well your code performs.
And that really leaves us with one final thought. We've just built this amazing toolkit to sort and search with incredible efficiency. So, what else can you do with these skills? You could find all the common elements, the intersection, between two massive lists. Or you could combine them into one big, unique list, their union. The fundamental principles are exactly the same, and the possibilities are absolutely endless.